Hello, everybody. Welcome back to another Astro Coffee Hangout. My name is Tony Darnell. I'm from deepastronomy.com. And this week we're going to be talking with some researchers from the Space Telescope Science Institute about hot Jupiters. They've been doing some looking at what causes some of the upper atmosphere features that we're trying to understand, and they've been using the Hubble Space Telescope to do that, and they have other data as well that they've been using, and they've got a paper coming out soon that discusses what they found with the formation of some of the features in the upper atmosphere of hot Jupiters. We're going to talk about that with our guests here today. But before I get started, I want to do what I always do each week, and that is introduce my co-host. Her name is Dr. Carol Christian. You guys remember her. Hi, Carol.
Hello.
Hi. So you're in South Carolina right now.
I am. Behind me is the great state of South Carolina. And I'm at the South Carolina Commission for the Blind, and we're doing some STEM education in astronomy using assistive technologies, which is pretty interesting. Anyway, that's what I'm doing, teaching this week.
That's really great. So why don't you give people a little background on what this hangout is about, what we're doing here, and what we hope to accomplish each week.
Sure. So in science departments, especially astronomy departments around the world, we often have something called science coffee. And so we all get a cup of coffee and we meet, often in the library or a conference room, but it's usually near a coffee maker. And we talk about the kind of research we've been reading about. We talk about a lot of other stuff too, but we talk about the research that we're reading about. And we thought, boy, it would be really interesting to broaden the audience for these discussions, because you get to see a little bit behind the scenes on what researchers are doing, how they were thinking about putting their project together, and things like that. So we thought, well, instead of Tony and I just talking about it and having a cup of coffee and with Carl, what we would do is we would invite researchers in to talk about, so we could hear right from them how they did the research, what they found, what they were thinking about, and what they're going to do in the future. And so we're really fortunate to have some folks who recently did a press release on this, and pretty interesting, separated at birth, sort of Jupiter-like planets that are very different, but they're also sort of the same. So I became intrigued in the subject and thought we should learn more about this. And I want to say that this is sponsored by the American Astronomical Society and the American Astronautical Society. So we often on these hangouts get both the engineer and the science researcher point of view.
That's right. Good. Thank you, Carol. Okay, so our topic today is hot Jupiters, like we talked about in the intro just a moment ago. I want to let you guys all know that we are live streaming on YouTube, Facebook, Twitch, and Periscope, and we are monitoring all those platforms. I have the live chats open for YouTube and Twitch right here, as well as I have the Facebook page that I go to periodically throughout the Hangout. So please leave our guests questions and comments if you have any. Already a lot of people are on the YouTube live chat. I see John Suffold is there, and Galaxia, Ascanto Vitale, and others. Darth Chocolate is here. So yeah, that's great.
Hooray, welcome.
Yeah, so Galaxia is saying, hello, Carol. I don't know how many R's are needed here, but South Carolina.
Just one, but thanks.
She's got several in her text.
Okay. Hey there.
South Carolina sounds like a beautiful state. Probably something to do with songs of John
It's been raining the whole time, so I'm like, what? So anyway, it's going to get better as soon as I leave. No worry for South Carolinians.
Yeah, that's probably true. Okay, so anyway, as you guys can see, I am looking at this, so please leave your comments and questions for the guests. So with that, let me go ahead and get started by introducing my guests. I'm just going to go from right to left on my screen here. First up is Dr. Giovanni Bruno. He is a postdoc and a member of the Exoplanets Atmospheres group. He works with the Hubble Space Telescope team there also. Hi, Giovanni, and welcome.
Hi.
It's good to have you on our Hangout. Also is Dr. Kevin. I have to do a lot of clicking here. Dr. Kevin Stevenson. He is a research astronomer at STSCI. He works on a lot of things. He's also a member of the Exoplanet Atmospheres group, but he looks at Hubble data. He's going to be looking at JWST data when there is some to see. And, of course, he says you're also looking at Spitzer data, right?
That's right.
So you got your fingers in all kinds of data pots.
I try.
Okay, cool. So great. You got the exoplanet atmospheres group. That sounds like a pretty cool thing to be a part of. I think, why don't I start with, I'm not sure, I should have asked this before we started. Which one of you is the lead author, or should I ask about a summary of the paper first? Would that be you, Kevin?
Giovanni's the lead author.
Giovanni?
So
Okay, thank you. Go ahead, Giovanni. Tell us a little bit about the paper.
So this paper tells the story of two giant planets which orbit very close to their star. These are the main kind of planets we are able to characterize with Hubble. In particular, we're able to study their atmospheres. And so with this paper, we were concerned about cloud formation in their atmospheres. This is an important process that we understand only partially, and it's very important to understand how the atmospheric processes work in these atmospheres. And also with Hubble, we were able to observe how these clouds impact the shape of the spectra we observe. In particular, with Hubble, we're going to observe the absorption of water at 1.4 micron. And with when there's cloud in the atmosphere, we see a muting of this spectral feature. So what we wanted to do with this study is to take two planets which look very similar, apparently, for the properties we think impact cloud formation, which are their temperature and their surface gravity, and go and see if their spectra look as we expect them to look like, which means they should look very similar. And what we found out is that they don't. And we suppose that this is due to some formation processes which are not included in our modeling right now. So now we're considering just the planets as they are right now, but their history brought some other elements which we need to understand better in order to understand the difference.
Okay, now, guys, if we're going to unpack everything he just said, but so don't worry. There's a lot there that he just put out there. So let me start by backing up just a little bit and asking you guys, who wants to tell us what a hot Jupiter is first? These are, first of all, we are talking about planets around other stars. These are exoplanets. Some are bigger than others. As Jupiter, a Jupiter-sized planet, as you can imagine, is a big planet. So, Kevin, give us a little summary of what the heck is a hot Jupiter.
Sure, absolutely. So hot Jupiters are a class of planets that we consider to be orbiting very close into their parent stars. So typically something like orbital periods of less than 5 days. And so you can imagine, so Mercury has an orbital period closer to 40 days. So these planets are much further in, much closer to their stars than even Mercury is to our own sun. And because of that, they are highly irradiated. So these planets are over 1,000 Fahrenheit. And so they've got huge amounts of heat coming in on one side, just blasting it. And this allows the atmospheres to get really hot, and they have different types of clouds than what we expect. On Earth, we have water clouds, but these planets, because they're so hot, they have different types of clouds. And that's really the question that we're trying to understand is, although these planets are very similar, they appear to have different types of clouds.
They're similar. They're similar to each other, you mean?
Right, exactly. So they're both the same temperature, have similar gravities, they have similar parent stars. So one would imagine that they are, in a sense, like cousins. They have this sort of similar environment in which they are in. But as it turns out, when you probe the atmospheres, they're very different.
Okay, but so we're talking about planets.
I just wanted to remind all our listeners that astronomers are extremely technical and clever about their nomenclature.
Always.
So if it's like a Jupiter and it's next to something hot and its atmosphere is hot, we call it a hot Jupiter. It's a very technical term.
Well, and but hey, if it works, it's descriptive, right?
I know. We always name stuff like this. There's nothing mysterious about our naming. Okay.
It works when you know something you have something to compare it to, right? Otherwise, it's very difficult. You don't have it.
Absolutely. It's like Jupiter, but it must be hot. Exactly.
Yep.
So, Kevin, we're talking about stars that are big, they're large, and they go around their star. How fast? Did you say once every what? How many days?
Every 5 days. That's about right.
Yeah,
5 days.
Yeah. About every 5 days. And you said that they are more or less the same as they are more or less the same as each other, with differences that you're finding in your research, but they tend to be around the same kind of star. Is that what you also said?
So these two planets just so happen to be orbiting the same type of star.
Okay, but exoplanets is a generality.
As a generality, planets orbit all different types of stars.
Okay, good. So you could see a hot Jupiter around maybe a red dwarf star?
So we at least see them around K dwarfs. So F, G, and K dwarfs, we see hot Jupiters. What we're tend to seeing around the M dwarfs is slightly smaller planets, like Neptune size.
I see.
So the smaller stars produce smaller planets.
But these are all roughly the same size as Jupiter, though.
The ones that we're looking at, yes, both of them are both the same
Okay,
size.
now are they hot? And then I'll move on to some of your research here. Are they hot because of how close they are to their star, or are they hot because they have internal processes that are heating them up?
No, these systems are fairly old on the billion-year time scale, so there's no sort of internal heat that's causing them to be warm. It really is the star that's heating at least one side of the planet.
Because is that because they're tidally locked, usually being that close together?
Yeah.
Okay. I just can't. So okay, let's talk about the atmospheres of these things then. How do they keep? They're mostly gas, I assume. If they're like Jupiter, they're mostly a gas planet.
Yep, hydrogen, helium dominated, very much like Jupiter, as if you'd taken Jupiter and kind of moved it in towards the sun inside of Mercury's orbit. And then from there, if you do that, if you imagine these stars probably formed further out in their solar system, and migrated in. And that's the planet formation question that we have is, could these planets have formed at different spots, at different points in their respective systems and then migrated in? And because they formed at different regions, maybe their atmospheres have different compositions, or maybe they have different types of clouds in their atmospheres.
Okay, and so you guys are looking at these with HST to try and see if that's true. Now, Giovanni, you said that you picked a couple of planets that you thought were more or less the same, right? The hot Jupiters, and then you looked at them. You were looking for a special feature, though, called water vapor.
Yeah.
And this water vapor we have it in our own atmosphere. That's what clouds are. So we know what water vapor is. And you said you looked at about, what was it, 1.4 microns. That's in the infrared, correct? All
yes.
Right. So you look at these and the Hubble Space Telescope is a really good infrared telescope these days because of the Wide Field Camera 3. What instruments, first off, did you use on Hubble to find these? Was it Wide Field Camera 3 or was it something else?
Before Wide Field Camera 3, there were other instruments, but right now I think it's the main one which is used.
Okay, and your paper, in your research, you said you're trying to understand how these upper atmosphere cloud formations come about, right?
Well, I would say the purpose of the study is more to say we have these observations, and from the observations we deduce the shape the spectra have and the basic atmospheric properties we can derive. But understanding the models of cloud formation is out of the purpose. It's more we think the story goes this way, but we're not doing modeling. Okay,
so and here you go. You're looking at two planets. Were the two planets you were looking at, were the stars the same?
The stars are very similar in the sense that they have a very similar temperature, which is the thing we are interested in the most in, because it determines the temperature of the atmosphere in the end.
And what were the orbital periods of the two planets?
It's slightly less than 5 days, both of them.
Okay.
And the stars are a little bit colder than our sun. It's about 5,200 Kelvin, while our sun is 5,700.
Okay, so Carl has one of your slides up here of two apparently similar planets. So if you click on his thumbnail, it'll get big for you. So you looked at WASP 67b and HAT. How do you say that?
Hat P.
I knew you'd say Hat P.
It's all names.
All right, so one's a hot Jupiter and one's a hot Saturn. Now, we didn't talk about that.
Well, it just means that Hat P38b is a little bit smaller than WASP-67b, but what we're really interested in is the combination of mass and radius of the planet, because the two of them give the surface gravity, which is a measure of the acceleration on the surface of the planet. Well, these are gaseous planets, so defining the surface is not like for rocky planets. We use a reference pressure to say, oh, okay, here we put the surface. But surface gravity is the measure of the acceleration that you have, like also here on Earth. So here on Earth is about 10 meters per second. It means if you fall, in 1 second, you gain a speed of 10 meters per second. And on this planet, the surface gravity is more or less similar to the one of the Earth. This is the property we're interested in. Mass and radius by themselves don't tell us too much.
Well, that's interesting. So you're telling me that you define the surface of a gas planet by where the pressure is, where the pressure would be. No, wait a minute, that's not right.
No. You say, so, correct me if I'm wrong, but rocky planet, it's easy to define a surface because it's when from a gas atmosphere you get that rock.
Right. But you said something about pressure. You use a pressure standard.
For a gaseous planet, you say you have an increase of temperature as you go deep in the atmosphere, and at a certain pressure, you say,
that's a surface.
Okay, I put my surface there.
Okay. What is that?
Yeah.
Is it just a number?
It's 10 bar.
10 bar.
So 10 bar, regardless of the size of the planet, that would be the surface. That's interesting. I did not know that. Okay, cool. So, but the thing that Carl, can you put that back up again? What you just had. So the fact that this was just a hot Saturn, all that really meant was the density was a little bit different, the gravity was a little bit different.
It just means that the size is a little bit smaller than the other one.
Okay.
But
the gravity is the same.
But the gravity is the same. The temperature is the same. So for the purpose of atmospheric modeling, these two planets are more or less the same.
Okay, so you're saying the temperature equilibrium, the equilibrium temperature, and according to this, is 1300 Fahrenheit. You've looked where the G force is right about at Earth, like what you said. They orbit the star at about 4.6 days. So this is laying the case that these are apparently similar, but you say they're not when you look at them with Hubble.
Yeah, and
do you have another slide?
I think in the next slide.
Can you put the next one up for me, Carl? Yeah, just scroll down.
So this is a slide that tells you how we measure the what we call the transmission spectra, which means...
Okay, so you use the transit method then to see...
Exactly. So we're looking at a transiting planet, and we observe the transit in different wavelengths. So when a planet transits in front of the star, we have a dimming of the starlight we receive, and in different wavelengths, we will observe a different amount of absorption because there will be different molecules in the atmosphere, and the light of the star passes... A part is blocked by the interior of the planet, and a part passes through the atmosphere. So, and in different wavelengths, we will have different molecules which absorb a different amount of light. As a result, if we repeat this process for many wavelengths, we will have different amounts of absorption. And this is what we call a spectrum, the amount of dimming of starlight. So, this is what you see in this slide in the bottom are the transits in one of the bands for both the planets. So you see how they look well. And then in the following slide, there's the result, how the transmission spectra, how it looks like. Yeah, so you see you have the spectrum of HAT-P38b on the top and WASP-67b on the bottom. And what we are interested in is the amplitude of the absorption of the spectral feature, which is in the yellow square. Water is there. So the largest, the widest this feature is, the clearer the atmosphere is. And we can measure the amplitude of these two features and compare them, and we see you can see it also by eye, but you can quantify it. And you see that WASP-67b has a muted, which means it's less wide absorption feature than HAT-P38b. So the most likely explanation is that.
Well, first of all, that was a surprise to you, right? The fact that those are different. Okay.
Let's call it a surprise. Yeah. Because models tell us all things equal, things look equal. So, yeah.
So all things are not equal here. So I'm sorry.
Let's say part of us was expecting that. Oh well, we're not modeling everything, so probably we're going to find something that we're not expecting.
So the fact that you see two different spectra here, and these are observations. This isn't a model.
Yeah.
The fact that you're seeing two different results tells you that there's something in your models that you're not accounting for. But that's not a surprise because what do we really know about hot Jupiters anyway? Do we know? We don't know.
We know something.
Okay. Well, why don't you tell us what we know?
Well, what we know.
We know they have water, water vapor, anyways, not maybe molecular water, and we know that they have clouds. And in fact, based on what we've seen with all the data, we believe that probably all of the hot Jupiter planets have clouds to some degree or another. And so really it's just a question of maybe how thick those clouds are or how patchy those clouds are, whether or not we see them with the transit observation that Giovanni was talking about, because we're sensitive to certain parts of the atmosphere with that measurement as opposed to other types of measurements. But more or less, we know that there's lots of clouds in all planets, and it's just trying to figure out how the clouds are affecting our measurements in these two systems and all of the other systems as well.
Okay, so you can really help me out here. I would like to understand why it seems that the spectra which have flatter features are the ones that have clouds. It just seems counterintuitive. You would think if there's stuff, it would show up. So clouds really dampen out any large fluctuations in the spectra. Is that correct?
Well, because what you're observing is the amount of starlight which passes through the atmosphere. So imagine you have the inner part of the planet which blocks the light and the atmosphere on the top of it. And if you have a cloud, this cloud is going to block more features. So as a result, what you're going to observe is
so the light can't actually penetrate down farther enough to produce those features and then come back up, whereas if there's a cloud, it just stops.
Exactly. Clouds have radiative absorption properties which are different from the rest of the atmosphere, and so they dim the absorption which would instead be there if...
It essentially cuts off the bottom of the atmospheric feature, so you can't probe as deep within the atmosphere because the clouds are blocking that, so you can only see at that point and above.
Ah, okay.
Yeah.
All right. So what do you think? What about? Okay, so you looked at these in the water vapor lines, and you saw that they had different amounts of water vapor, but. Come on, aren't Jupiters made of different things? Do you expect? Wouldn't the gaseous composition of each of these planets be a little bit different and maybe other elements? So, like, I don't know, ammonia or other kinds of things.
Yeah, we need a lot of lines to say that.
You need to what?
We need a lot of spectral lines, and for the moment, the main molecules we are interested in, besides hydrogen are oxygen and carbon. And that's why observing water is that important, because you have hydrogen, you have oxygen. And with oxygen itself, you have an important information, but not enough to say what's the average composition of the atmosphere. If we were able to observe also carbon absorption lines, we will be able to tell much more. So that's our limitation for the moment.
Okay, and that's just an instrumentation issue. You want with future observations with other telescopes, you might get more information.
Yeah. For example, James Webb will tell us something more about carbon.
Okay, cool. And
on a broader sense, the amount of carbon and oxygen and nitrogen within the atmospheres of a planet is really defined by the disk in which the planet forms. So and that we can get a sense of what those ratios are based off of the metallicity of the star. So if the two stars have similar metallicities, by metals we mean anything, in astronomers we mean anything other than hydrogen is a metal. So helium all the way
right,
through.
we've talked about that, yeah.
So if we know what the metallicity of the host stars are, and those are the same, then it's most likely that the disks in which the planets formed also had similar metallicities. And therefore, we could expect that these planets would have at least similar carbon, oxygen, nitrogen ratios in their atmospheres. And because these planets are very hot, remember, the chemistry that goes on within these planets is very quick. So we say it reaches equilibrium, chemical equilibrium. So that any molecule that's produced that shouldn't necessarily have a long lifetime would immediately sort of go back to its equilibrium state. So we usually have, water, CO2, those sorts of molecules in abundance because those have the lowest energy.
Okay. Let me get to a couple of questions here. Cello Fingers is asking, would these hot Jupiters have moons?
We would like to know.
Yeah, most of the time, hot Jupiters do not have moons, simply because they're gravitationally unstable at these distances. You would really have to go much further out from the host star to have a moon that won't get stripped away. That doesn't mean that these planets didn't have moons at one point in time, but they don't anymore.
Okay. And Asciano Vitale is asking, if they are tidally locked, I wonder how these moons could orbit being so close to the star, and that was a follow-up to that, so they probably don't. Cosmic Stardust is asking, I saw somewhere that our own Jupiter was almost a hot Jupiter, but it was the birth of Saturn that pushed Jupiter out of that path. Is it possible that is how our planets ended up where they are?
That's a broader planet formation question, and yes. So it's possible if Saturn hadn't formed. So what happens is Jupiter and Saturn were in a near resonance orbit, and when they started migrating inwards, they hit that resonance, and then they started pushing back out again.
What's a resonance orbit?
Okay. So that's good. Yes. No, that's very good. I'm glad you asked. Okay. A resonant orbit is, I'll give you an example. A 2-to-1 resonant orbit means that the inner planet orbits twice every time the outer planet orbits once. And so the 2-to-1 is the 2-to-1 ratio of the orbital periods.
Okay.
And what happens is when you enter close to these resonances, the two planets interact because every 2 times one goes around, the second one will orbit once, and then they interact a little bit, and then they interact again and again and again near those resonances, and then they can basically push in and out in their orbits together in this resonance. And in this case with Jupiter and Saturn, it pulled Jupiter outwards, which could potentially have saved the inner terrestrial planets like Earth and Venus and Mars.
Do you think it saved it from being a hot Jupiter? Is that sort of begs the question a little bit to me, is that you said these hot Jupiters formed in the outer parts of the system and then migrated close toward the star. Do you think that's a natural thing for gas giants to want to do?
So what we're seeing, I will quote a study that Professor Heather Knutson of Caltech is leading. It's a study called Friends of Hot Jupiters. And what it finds is that a lot of the hot Jupiter planets have there are distant binary companions to the host stars. So basically, it's not just the star and the nearby planet; it's the star, nearby planet, and some distant star that we can see directly. And so what that tells us is that there's some sort of gravitational interaction that happened in the past when this Jupiter was far out there, 510 AU, between this binary companion that forced it in to become a hot Jupiter.
So you think they have to be forced in? They don't just drift in?
That is
left to their own devices.
One mechanism that we're seeing for these hot Jupiters. And there seems to be roughly half of the hot Jupiters have these friends, basically.
And these friends are these binary stars that are out there holding or interacting with it in some way. Throwing doesn't sound very friendly to me to be throwing it into the star, but
No.
I have a question then. So now with TRAPPIST and some of the others, we're seeing these multiple planetary systems. Those systems, they don't have hot Jupiters?
Right.
Okay.
Yep.
So the idea that the Jupiter migrating in could be the demise of interior rocky planets, as you said, and so it's lucky we don't have one. And some of those other multiple planet systems, they're lucky too that they're
very
planet.
lucky.
Okay.
All right. Let's see. My chat scrolled. I had some questions here I was going to read. Let me just look through. We already talked about the moons. I saw that some of our Jupiter. Oh, that's right. So Galaxy is commenting: the closer the planet is to its star, the faster it rotates. Plus a shorter orbit. It's both. So that's where the tidally locked issue is, where the rotation matches the revolution. Correct.
Right.
Mm-hmm. Okay. So and let's see. Bjorn Larson is asking, why are there surface features on the gas giants in the solar system? Aren't they almost only hydrogen and helium? Why do they have surface features at all? That's a good question.
Well, we don't see their surfaces.
Well, okay, atmospheric features. I think that's what it is.
And you said they don't?
Well, the planets don't have surfaces, right? But they do have atmospheric features that we're seeing, right? So when we think about Jupiter, right? Those images came out about Jupiter a week or two ago, and yes, those have exquisite detail. These features that are happening, they're not on the surface, the visible surface, but not a rocky surface for these planets, and it's probably very likely that these planets, HAT P38 and WASP 67, have also very intricate, detailed structure to them. We just can't see that.
Okay. Adam Synergy is asking a good question. Are these planets oblate? Do they have tear-shaped atmospheres?
Whoa.
We haven't done the calculation yet. Chances are, when you have an orbital period of about 5 days, the level of oblateness is going to be quite small. Once you get closer into 1 day orbital periods is when it becomes significant.
Okay. And Chuck
1 day?
1 day. Yes, there are planets that orbit in less than 1 day. Several hour timescales, in fact.
That doesn't sound stable to me. Is that a stable configuration?
No. Chances are these planets, at least the ones that are 4 or 6 hour timescales, they are probably quickly on astronomical timescales, but slowly for us, spiraling into their host stars.
You know what's weird about these? The more I learn about exoplanets and doing these hangouts and talking with people who study them, is that it seems like our solar system is really kind of a weird one. I mean, we go out and we look at these things like Carol was saying with TRAPPIST-1. It's got all these tidally locked planets within, all crammed right up next to this red dwarf star, and then we've got our planets seem kind of benign by comparison. You've got these hot Jupiters orbiting in 4 days, and you're saying in some cases they can do it in one. What do you guys think? Is our solar system weird?
It's difficult to say because we're not really sensitive to our own solar system. So if you think about
okay, that's a great point. But you mean by the telescopes that we're using to observe with right now?
We have a biased view of the exoplanets, or of the galaxy as it is, because all of the systems that we can detect are highly dependent on which methods we use to detect them. So if we used transit method, then planets chances that are closer into their stars are easier to detect. If we use the radial velocity method, then we're sensitive to the higher mass objects. So it all depends on what method we're using. And if we optimize our, for example, direct imaging techniques with future telescopes, then I think we will find a lot more systems like our own.
Okay. Andrew Planet is asking. Oh, I'm sorry, Andrew. Andrew says on another Google account, the Facebook event page vanished after I made a comment that for some reason I wasn't receiving embedded event notifications. I don't know why. Yeah, I noticed that the Facebook stream died. I don't know what happened either, Andrew, but thanks for coming over from there. I'll have to look into it after the hangout. Chuck Rittersdorf is asking, what does a hot Jupiter mean for the complexity of a star system? That's just what we were talking about a little bit about our own system. If a hot Jupiter migrates in, do they mix the system up to a higher complexity, or do they clean up the system to a more simple state? And I would just offer that clean up is a relative term, because if I'm in one of those planets that's getting cleaned up, that's not so great. I wouldn't consider that being cleaned up. But anyway, what is your comment on that? Does it make things more complicated?
I guess it depends on your point of view, right? It kicks out a lot of the planets that were potentially had formed there, because he's the big guy on the block. He's the bully. He's not going to go anywhere, except for maybe that binary who's a little bit further out pushing him in. But yeah, so he's going to knock around all the smaller guys and kick them out or force them into the star.
Okay.
Sounds like the playground in high school for me.
Yep.
Also, when it comes to weirdness, do we really know what is weird? I mean, people are all strange. Solar system might be very, very similar.
That's a good point. Yeah, we don't really have a good statistical count of anything, but I do like the point that we are biased in what we're seeing so far. We have to remember that, because our telescopes can only see certain things. That big planets are way easier for us to see than tiny planets. Planets that are close to their star, blocking out the light all the time, and the transit of their orbits is easier for us to see, because we don't need to be staring at them for 100 years to be able to see if there's one there or not. So that is a great point. And hopefully with new telescopes, survey telescopes like TESS and others that are looking at the whole sky for a really long time, we'll get a better idea of the statistics of what is normal and what's not. Adam Synergy is asking a good question. Do we know what percent of stars have hot Jupiters? And I want to expand that by what is the most common star that has a hot Jupiter?
So
yeah, main sequence stars which are also the easiest one to observe for now, and I think
why are they easier to observe? Why are main sequence more?
Well, it's not it's not that main sequence stars are easier to observe, but it's easier to observe planets around main sequence stars.
Ah, okay, because of their brightness.
Because it's the ratio of radii or masses, which is the thing that defines our observational techniques. So you have a transit, or you have the wobbling of the star. So when you have not a giant star and a large enough planet, you see better.
I see, but so that's another bias, isn't it? So we can just happen to be able to see these around these kinds of stars better. So do you have a guess on the percent of all stars that might have a hot Jupiter?
There is one which I never remember, which is
it's less than 1%. Yeah, it's a small fraction of the systems that actually contain hot Jupiters. And so although a lot of the planets that we've discovered and characterized are hot Jupiters, they are actually one of the rarest types out there.
Oh, they get much better press.
They do. Yeah. Well, when we have the Hubble Space Telescope to characterize their atmospheres, they're the ones that get all the attention, right? And I think TRAPPIST got a lot of good attention with the TRAPPIST-1 discovery, and I think with a telescope like James Webb, we'll have a shot at characterizing planets like TRAPPIST-1c or TRAPPIST-1d. And so I think those smaller planets are going to start getting a lot of attention soon.
Okay.
I have a quick question that you kind of brought up, like, how do we know? So you said that we have the tools to kind of find and characterize these hot Jupiters, but we have an idea of that they're not the most common. They make up like 1% of the planets out there. How do we know that there's that discrepancy? I mean, obviously there's our bias with our tools, but then how do we figure out, all right, this is where the discrepancy exists?
Because when we look for planets, we look for many stars, and we see also those which don't have planets. And there's a geometric probability for a planet to give us a transit or be observed in radial velocities or stuff like that. And so we can extrapolate from statistics. And Kepler had up a lot in that because he observed a lot of stars. And so one can have an idea of how many stars in the field we observe have planets and how many don't, and of which kind.
Yeah, as it turns out, the most common type of planet is probably closer to a super Earth or a mini Neptune. So that means, somewhere like 1.5 to 3 times the size of the Earth.
Yeah, we were talking about that in several hangouts with what the most common kinds of exoplanets are. Rad Dad has a good question I'd like to know that I'd like to ask as well. He goes, if the hot Jupiter formed further away from the star and migrated closer, why did it stop and not just fall into the star? Why didn't it just keep going? That's a great question.
I think it's debated. I think it was thought until recently that there's some dynamical mechanism which makes so that the planet arrives until a certain point and then reaches an equilibrium. And so it stops there before falling into the star. But then I think that's an argument that has been just put in other versions with interactions with other bodies on the disk. And so I'm not sure whether there is a clear picture.
Yeah, the going theory is basically what Giovanni described, is that it reaches a pseudo-equilibrium in that several-day orbital period range, where it just happens to spend more time there than not. And so it can hang around for a while at 4 days, and then it can migrate inwards and then get bumped outwards in that several-day orbital period range, and then eventually it just happens to star.
So I was going to ask about that, whether there is evidence for these type of objects migrating out. I mean, is there a whole distribution of distances, or do we just not have the observational constraints to answer that question?
It's the migration timescales are very long, so we need long baseline observations to measure that. We're looking for that, so people can actually measure the transit times, and if you I don't want to get into the details, but more or less you can measure, if you keep track of when the transits occur, you can see that the period is either getting longer or shorter, and that'll tell you in which direction it's moving. So we just need a long enough baseline to make that measurement, and then we will see it on the order of 10 to 20 years for some systems.
Yeah, well, that is a lot of observations.
Okay, so I'm on the live page at Deep Astronomy. Sorry, Larry, I was there. I just didn't get a chance to call it up until just now. He's commenting, Io is Jupiter's closest moon. Is it orbiting close to the planet? Or it is orbiting close to the planet. It is also leaving a sulfur gas in its orbit. And his question is it possible to see anything in the hot Jupiter's orbit? So we talked about moons. They probably don't have any. But what about that? As as it's orbiting the star so close, is it trailing anything?
Most likely, yes. A lot of the planets that are that close in and that hot will be evaporating hydrogen. And obviously, the hotter you are and the closer in you are, the more hydrogen you're evaporating. So there are other planets that are twice as hot as this one, that basically their entire I don't know. If I say Roche lobe, you're going to ask me what that is. So, the entire planet and its gravitational bound region is emitting hydrogen, and the hydrogen is basically escaping more like a tail of a comet than for this planet in this case. But those planets are much hotter than the ones that we're talking about. But it's possible.
Okay. And he was also asking, Larry Keese was on the YouTube chat because he moved over there because he thought I wasn't looking. He was asking, does the ratio of star size to planet size matter? Does the transit process cause some planets to not be observable? Well, okay, there's two questions there. So the first one, does the ratio of star size to planet size matter?
That's the most important factor.
In our observing it.
Measuring. Sorry?
In our ability to observe it.
Yeah, in the sense that if the planet is too small compared to the star, then we're not going to have the precision to observe its transit. And that's what happens for like a planet as large as the Earth, orbiting around a star as the Sun at the same orbital distance. We wouldn't be able to see it.
Right, but what I've learned in this hangout, that does not preclude a hot Jupiter being in orbit around a blue giant. We just can't see.
No. It
only that ratio matters, I guess.
Allowing that, then yeah, they should be around, but it would be much more difficult to observe them. I think, for example, there's this ESA mission, European Space Agency, which is Plato, and which is planned for the 2020 something. And I think in their plans they have to try and observe also some planets around giant stars.
Oh, okay. And to follow his follow-up question, does the transit process cause some planets to not be observable? I think what he means is that because the transit method involves a line of sight kind of issue, there's a bias there. We only see those planets that pass in front of the star between us and the telescope. So there's probably many more that we're missing, correct?
That's the geometric effect, the geometric thing that I was talking about before, in the sense that of the planets that we observe, transited, there's many which are around the star but don't transit.
Yeah, so I think if I didn't get that right, Larry, just because I think you might have meant something else. If you meant that it knocks out other planets or something, just clarify in the chat so we can.
And I do apologize. I have to go catch a plane. But thank you so much,
Carol. Thank you for doing
the hangout, and have fun for the rest of the hangout.
All right. Thanks for joining us, Carol. We'll see you next. We'll see you next week, right? We'll see you next week. Okay, cool. See you next week. All right. Take care. Bye bye. Okay, so
going back to his question, I think he may have was thinking about the radius ratio and the transit combination. So if the radius ratio is too small, then there are planets out there that do transit, but we're just not detecting them because the size ratio isn't favorable for us. So, for example, as Giovanni said, an Earth-sized planet orbiting a sun-like star isn't as good as an Earth-like planet orbiting a small M dwarf, for example.
Oh, okay. So, all right. Christopher Pedersen is asking, if a planet gets thrown out of a system, is it more likely that it will get thrown out into deep space or into an orbit similar to the proposed planet X? So that's a little bit outside of the realm of what we're talking about, but those are possible outcomes. Either you could get ejected and become a free-floating planet, or you could just get bumped out to a higher orbit, or bumped into the star, right? Pushed into the star. Those are three different outcomes that could come about. Okay, and there is a from Cello Fingers. Would there be a possibility of floating extremophiles? And if so, could spectral analysis give any clues? That's going extremophiles. That's life on these hot Jupiters. And I guess let's first talk about what your opinions are on whether these things can even have life, and if they do, they would probably be extremophiles. But what do you think? Can anything be floating around in the upper atmosphere?
The extremophiles that we know on Earth, I think, can survive until something like 400, 500 Fahrenheit. Something like that. Or maybe I'm wrong, but these planets are way higher than that. Way more.
That's right. What within that slide? What was it? 1700 Fahrenheit, something like that.
1300.
1300. Yeah. So it was.
So I mean, maybe we for sure we don't know what the possibilities of life are, but for life as we know it, is very unlikely. Okay. All these things said, there's a. I assisted to a talk of a theoretician doing exoplanet atmospheres. I don't remember his name but he was saying the difference between a biologist and an astronomer is that the biologist says what are the spectral features produced by life, and the astronomer says what can I do to try and prove that this is not life, that there's some non-biological process producing the same thing. In the end, we're not able to see extremophiles for real, but just their products. And so
that's right.
One can always say, I can model the spectroscopic emission of some life, and somebody else can say it can be something else. So
yes, and I would offer Cello Fingers to look at our ExoLife Hangout on Wednesday nights, where we've talked about this in several capacities. So yeah, there's a lot. That's a good. I never heard that though. That astronomers and biologists are looking at the same spectral lines just for different reasons, I guess. So Atom Synergy, are these two hot Jupiters good candidates for JWST, and what molecules would you hope to see? Now you talked about that briefly, but are you going to look at this with JWST?
hopefully, yes.
And not just in water vapor, though, right?
No, first of all, carbon-bearing molecules. Because, as I said, with water we have oxygen, and with carbon we would be able to say something more about the position in the protoplanetary disk where these planets formed. And so we would be able to say something about their formation, something better about their composition, and so their processes on their interior. And then there's another thing with by observing farther in the infrared with an instrument called MIRI, which will be on James Webb. This will tell us something more about the composition of the clouds themselves. So there are many different kinds of clouds, and for now, with the main planetary properties, we're able to say, oh, maybe it should be this or that, but we will be able to observe them with James Webb. I think we could do with HST right now is going, instead of red, going blue, and so going to the visible. Because in the visible wavelengths, we have other information on the clouds and other kind of aerosols which are present in the atmospheres of these planets, which we won't be able to observe with Webb, because Webb will only go in the infrared, and this information is only in the visible.
Okay, and I'm just reading some of the comments. Steve Jobs, actually, the way you've spelled it. I feel like if a Jupiter starts making its way inwards, he isn't going to sit in a steady orbit and will either sling out and or dive to the sun. Okay, well, we've talked a little bit about that. Susan Hunter is commenting, in less than 100, or it's a question actually, in less than 100 years, we've gone from nebulae to galaxies to exoplanets in 100 years, and that's a good point, because 100 years ago, or maybe a little more now, we didn't even know there were other galaxies besides the Milky Way. We just thought they were all nebulae within our own galaxy. And then we've gone from seeing hundreds of billions or trillions of galaxies in the universe to finding exoplanets. And then we found that not only are there exoplanets out there, there's like on average 1.6 of them around every single star in our galaxy. And we've only found that out in the last 25 years. And so our question is, when are we going to see exomoons and dwarf planets? When are we going to be able to detect those? You guys have any comments? This is speculation, of course. But it's all about, to me, it's all about telescopes, isn't it? You need bigger telescopes. Exomoons are tiny. We barely can image exoplanets. I mean, even just barely with what we've got now. So a moon would be even orders of magnitude.
It's a combination of telescope size and telescope time. If you were to take the James Webb Space Telescope and point it at a specific system that you knew had a Jupiter-like orbit, you could look for the Galilean satellites, and you would probably find them with enough time. But those planets are very difficult to find, and it's very difficult to search for them with a smaller telescope, for example, something like Kepler or TESS, where we're not really sensitive to planets that far out in their orbital periods. So, you know what? TESS might be able to do that because it has what they call a continuous viewing zone, where they'll be looking for the same. They'll be looking at some patches of the sky for a few weeks, and other patches of the sky for 365 days. So in those patches, there's a chance that we could detect exomoons.
So TESS is the Transiting Exoplanet Survey Satellite. It's getting launched in 2018, March, I think, and it's going to look at the entire sky for many years and try and do these. And I'd forgotten about that. There are parts of it that's going to see all the time. So who knows? Who knows what it'll be able to image? The point is well taken, though. Kevin is like, we need to not only have big telescopes, we need to stare at this same patch of sky for a long time too. So to get the details out of it. So who knows? Who knows, Susan? Maybe we'll get to exomoons, but right now I'll be happy with just getting some of these regular, even hot Jupiters imaged at this point. So good. Well, okay. Well, let me ask you this with your research then, guys. What's next? What are your paper's coming out where you looked at these two Jupiters and found surprising differences where you expected similarities. What's the follow-up? What are you going to do after this?
Well, there's two parts. One, if we're lucky, we'll get some observation time in the visible for these planets with Hubble. So we will be able to understand a little bit better how these atmospheres are made. And on the other hand, these two planets are observed as a part of a much bigger effort, which is sampling a large parameter space. So these two planets are very similar, but there's a wide variety of planets with different temperatures and different surface gravities. And we are only starting to understand how atmospheres, cloud formation, and all these kind of processes work. So next there will be other planets in this parameter space with their peculiarities, and
so just to try to see more hot Jupiters in the same way that you did this one. But why? I guess just real quick, why do you want visible light images? What's that going to show you?
I'm sorry?
Why do you want visible light images?
The visible is going to show you scattering, which is one of the ways light is deflected by molecules in the atmosphere. So this will tell you something about the size of the molecules that compose these aerosols, which is a very important parameter for the models.
I see. Okay, good. Well, all right. So, Carl, just anything on Twitter that we've been missing, or have you been?
I haven't seen anything on Twitter,
okay.
And I've been looking at Twitch. There hasn't been anything.
Yeah, I've been looking at Twitch too.
And there was one question I thought that was kind of interesting, a concept of, and this is again kind of going into those really weird speculative questions. So it is what it is. But I thought it was an interesting idea of, one, could you possibly have two large gas giants that kind of orbit around each other, semi-similar to how Charon and Pluto almost orbit each other? And would them being close to their star destabilize such a configuration? And I have one other question if we have time for it after you guys answer that one.
So you mean a hot Jupiter, which is a moon for a hot Jupiter?
Yeah, basically is what the question is. It's like, would they remain stable in such a strange, fast orbit around their star, or would them migrating close, destabilize that kind of binary configuration where they'd be orbiting around each other?
Well, if there are some binaries, brown dwarfs, we have some similar examples that we already observed in rare cases.
WASP-12 is an example. So WASP-12A, the host star, has a hot Jupiter, which is WASP-12A lowercase b, with a one-day orbital period. But then there's WASP-12 lowercase or uppercase b c, which is a binary companion that orbits much further out. So you can't have these binaries, these kind of like M dwarfs or brown dwarf binaries, further out. But once they get closer into the host star, it would be very difficult to have a stable orbit.
Okay. All right. Well, I'm gonna have
one quick.
Okay, go ahead, Carl. But then I gotta cut it. We're already at 4 o'clock.
I know we're out of time, but there's this one last question I think is really great. So since they're so close to their star, this kind of pertains to the actual observations in your study. The stars have coronal mass ejections, all that kind of other good stuff. How do you make sure that your analysis of the planets aren't contaminated by the stuff the star is giving off?
There are some indicators of the activity of the star, which come from the spectra of the star, mainly, and from their photometry, not only inside the transit, which tells us that these two stars are not particularly active. So we are quite confident that the observations are not affected by an important amount by this.
All right, cool. cool. Thank you.
Yeah, thank you. All right. Well, we are out of time, everybody. I'm going to stop right there, but I want to just I want to thank our guests, Dr. Kevin Stevenson. He's a research astronomer at the Space Telescope Science Institute. He's a member of the Exoplanets Atmospheres Group, and also is Dr. Giovanni Bruno, also a member of the Exoplanet Atmosphere Group at the Space Telescope Science Institute, where they were studying hot Jupiters. And today we were talking about their paper of 2 different hot Jupiters, where they got some surprising results where they expected them to not be so different, and it turned out that they were. So I want to thank you both for being on our Hangout. I hope you guys might consider coming back when you got some more information for us. You got some more stuff?
Sounds good. Sure.
Awesome. Thank you very much. I'm gonna stop with a question from Tim Hem, who's going, how is the search for Planet 9 going? I've not heard much about that recently, and the only reason I'm reading your question, Tim, is because I just got an email from Alberto, like 2 minutes ago, that said that the title of this email is "Goodbye, Planet 9. New and better data disfavors a giant world beyond Neptune." I haven't read the email yet, but I'm about to, and if it's anything really cool and interesting, I'll be putting it on Space Fan News this week, so you'll learn more about the status of Planet 9. That's what I love about Alberto. I get all this stuff from him all over the place. So, all right. So thank you, Carl. I appreciate the work you did today on our Hangout. And next week, we are going to be talking about... Let me pull up next week's. Next week's is Astro Coffee Hangout, where we're going to be looking at galaxy alignments that are traced back 10 billion years. The most massive galaxies in the universe have been aligned with their surroundings for the past 10 billion years. It is the furthest back in time that this phenomenon has ever been seen. We're going to talk about the latest results from these very far away galaxies. You can bet the Hubble Space Telescope is involved. So anyway, that'll be next week's topic. We hope you guys can make it. Same time, 3 o'clock Eastern Time on Thursdays on deepastronomy.com. Okay. Well, with that, folks, I want to thank you all very much for watching, and as always, keep looking up.